Welcome to Lucid Mind Chemistry channel. In this video, I'll be solving Chemistry A-Levels Structured Questions, Paper 41 from May-June 2021. For question timestamps and other useful information, please visit video description. Question number 1. The carbonates and hydroxides of group 2 elements show similar trends in thermal stability. Suggest and explain the variation in the trend in the thermal stability of group 2 hydroxides. Now what happens in carbonates is that in carbonates of group 2, as we move down in the group, the stability increases. And the reason is the size of cation. Because anion is the same, there is no change in anion, but cations are changing. We have magnesium, we have calcium, we have strontium, barium. So what happens as we move down in the group, the size of cation increases. And now polarizing power, it depends on the size of cation. Polarizing power is inversely proportional to size. Greater the polarizing power, lower will be the thermal stability, because the anion is easily polarized by greater polarizing power. So what will happen that the elements in the top, for example, we have calcium carbonate, we have barium carbonate. Now among these, the size of calcium is smaller and it has greater polarizing power, while barium is larger in size comparatively and it has less polarizing power. So carbonate, in barium carbonate, it gets less polarized and therefore there are less chances for it to break. While the carbonate present in calcium carbonate, it gets more polarized because we have cation of small size. So when it is more polarized, what happens that the bond between carbon and oxygen, it breaks and oxygen goes towards metal. So when metal carbonate is decomposed, it forms metal oxide along with CO2. In the question it says that similar trend is seen in thermal stability of group 2 hydroxides. So hydroxides can also be explained on the similar manner. So we can say that down the group, group 2 hydroxides become more thermally stable. And the reason is similar. Because as we move down in the group, what happens that the size of cation increases. And polarizing power of cation will decrease. So larger cations cause less polarizing of the anion. And in this case, anion is hydroxide. So we can say hydroxide ions. Part B, calcium hydroxide is slightly soluble in water. Part 1, write an equation to show the dissociation of calcium hydroxide solid in aqueous solution. Include state symbols. We have calcium hydroxide solid, so we can write it on one side of the equation, OH. It is given as solid. Now this is a reversible reaction, which means that it is not 100% soluble. Some of it will remain in solid form. Now it can dissociate to form calcium 2 positive, as calcium belongs to second group in the periodic table, and hydroxide ions. Both are aqueous, as we are using water. Now we can balance the equation. We have 2 OH on the reactant side, so we can write 2 with OH negative ions. Part 2. Calculate the solubility in mole per decimeter cube of calcium hydroxide. They have given Ksp value, which is 5.02 exponential minus 6 mole per decimeter cube. Ksp can be written as Ksp is the product of the concentration of ions that are formed. So we have calcium positive 2 cations along with hydroxide anions, and as there are 2 moles, so therefore its power will be 2. This is the equation for Ksp. Now we can see the balanced equation. According to this equation, 1 mole of calcium hydroxide, it forms 1 mole of calcium 2 positive along with 2 moles of hydroxide. As the concentration is not given in the question, so we can write X instead of concentration for calcium, and if calcium is X, which is 1 mole, then hydroxide will be 2X, as there are 2 moles. So we can write X instead of calcium and 2X instead of hydroxide, and we have power 2, as there are 2 number of moles. So 2x squared, it will become 4x square into x, it will form 4x cube. Now we can put the value of Ksp on one side of the equation. We have 5.02 exponential negative 6. This is the value for Ksp. It is equal to 4x cube. Now we can divide 4 on both sides. We can also take cube root to cancel out this cube. Now calculating this, the value of x, it comes equal to 0.0107. So therefore this is the solubility of x, so we can write solubility as 0.0107 mole per decimeter cube. Part 3 suggests how the solubility of calcium hydroxide in aqueous sodium hydroxide compares to its solubility in water. Explain your reasoning. We have already studied the equation in water. Calcium hydroxide, it dissociates to form calcium 2 positive aqueous and hydroxide ions. Now what happens if we add sodium hydroxide along with water is that sodium hydroxide, it is fully soluble and it will form sodium ions along with hydroxide ions. Now the concentration of hydroxide ions is increasing. So when the concentration of product increases in a reversible reactions, what happens is that the reaction goes on the backward side and the solubility of calcium hydroxide will decrease. So we can write that the solubility of calcium hydroxide solid will decrease due to the common ion effect. Question 2, Part A, explain why chromium complexes are colored. Now chromium is a transition element, and for transition elements we know that the 3d orbital, it splits into 2 levels. One is low energy. For example, we have 3d XY, 3D YZ, 3D XZ, and second is 3D X square Y square and 3D Z square. So now there is small energy difference between these two. What will happen that the electrons, they can absorb energy to jump into the higher energy state, and then they will lose energy in the form of light, and this light lies in the visible spectrum, so therefore chromium complexes are colored. Now we can write the answer. Chromium complexes are colored because of splitting of d orbitals. Now what happens when d orbital is splitted is that the electrons, they get promoted to higher energy orbital. And this happens because the electrons, they absorb some frequency of light. And when electrons, they jump back into the lower energy orbital, complementary color is seen. Part B, 4 different compounds can be obtained when anhydrous chromium 3 chloride, it reacts with water under various conditions. When samples of each compound are reacted separately with aqueous silver nitrate, different amounts of silver chloride are precipitated. The precipitation leaves the complex ions P, Q, R and S in solution. This is the formula of compound that was used. This is the moles of silver chloride that is precipitated per mole of complex ion. So we have 3 moles precipitated, then 2, then 1, then 1. And this is the complex ion that is formed. And this is the property of the complex ion. Part 1, draw 3-dimensional diagrams for the structures of complex ions P, Q, R, S. So you have to draw 3D diagrams, include the charges for each complex ion. We can write the equation. For example, let's suppose we take this one and react it with silver nitrate. The equation will be like this. We have CrCl3H2O6. It reacts with silver nitrate, AgNO3. Now it says 3 moles of AgCl are precipitated, so we can write 3 AgCl. Now 3 moles precipitated means that 3 chlorine atoms are removed from the reactant, so the part that is left will be CrH2O6. So this is the complex ion P and it is nonpolar. Similarly, from this, if 2 moles of AgCl are precipitated, it means 2 chlorine atoms will be removed, 1 is still left behind. So the formula of product or complex will be CrCl, as 1 chlorine is left. We have 5 H2O. Similarly, for this one, we can see we have 3 chlorine atoms. 1 is precipitated in the form of silver chloride, so 2 chlorine are left. So it will be CrCl2 and we have 4 water molecules. And the last one, Again 1 mole is precipitated, so it will be similar. CrCl2 H2O4 complex. Now it says draw 3-dimensional diagrams, and also you have to write the charges for each complex ion. Let's find out the charges first. In the first one we have chromium. The oxidation state of chromium is +3, so we can write +3. And the oxidation state of water is neutral, so oxidation state is 0, so overall charge will be +3. In second one we have +3 for chromium, we have -1 for chlorine, so +3 and -1 it becomes +2. Water is neutral, so it is +2. In this one again we have +3 for chromium, -2 for 2 chlorine atoms, so +3 -2 it will form +1. So overall charge is +1 as water is 0. Again similar is for this one. Now let's draw the first one. We have chromium 6 water molecules, and in 3D diagram they already have given chromium in the center, so we can write all 6 water molecules. As oxygen makes coordinate covalent bonds, so we can write OH2 instead of H2O. It will be OH2 on this side, H2O on this side. And this is the octahedral complex. Now the overall charge, it was +3, so we can write +3 in square bracket. This is for P. Then for Q it is 2 positive, and we have 1 chlorine and 5 water molecules, and this is polar, so we can add chlorine, we can add 5 water molecules. Due to the presence of this chlorine, which is electronegative, this molecule or complex becomes polar. The charge is +2. Now third and fourth. In third and fourth we can see one is polar, one is non-polar, and the structures are similar as we have 2 chlorine atoms in both of them. Let's draw both. One should be polar and one should be non-polar. So for polar we can draw chlorine on one side like this. Rest are the water molecules. And for non-polar, the chlorine dipoles, they can cancel out each other, so we can draw them on 180-degree bond angle. Now showing the charges. Charge is +1 as we have 2 chlorine atoms. Again this is +1. Now R is polar, as we can see that both electronegative elements are on the same side, so this could be cis isomer. And as we can see that the chlorine atoms are on the opposite side, so therefore their dipoles cancel out each other, so this will become non-polar, and we can say that this is trans isomer, as the rest of formula is same. Part 2 suggests why complex ion S is non-polar. Again it is a similar explanation. We have 2 chlorine atoms in S, are positioned at 180-degree angle. So the dipoles cancel out. Part C, we have this question. The structure of picolinic acid is shown. We have nitrogen, we have carboxylic acid. The conjugate base of picolinic acid is a bidentate ligand Z. Define the term bidentate ligand. Now, ligand is something that makes coordinate covalent bond with the central metal atom or ion. In bidentate ligand, we have such structure that can make two coordinate covalent bonds with the central metal. So we can write the answer: species that donates two lone pairs to form two dative bonds with central metal or ion. Now it says draw the structure of Z. Z is the conjugate base of picolinic acid. Now we can first draw the structure. As this is picolinic acid, so what will happen that it can lose H positive. So the structure will be like this. We have nitrogen, 3 double bonds, COO negative. Now conjugate base means something that differs by a proton. So as we can see that there is a difference of H positive between picolinic acid and this structure, so therefore this is conjugate base. Now we can draw the structure of Z, which is the conjugate base. 3 double bonds are there, COO negative. Part 3, Z reacts with aqueous chromium 3 ions CrH2O6 plus 3 in a 3:1 ratio to form new neutral complex. State the coordination number and the geometry of the chromium 3 center in the complex. We have to find out the coordination number, which is the number of coordinate covalent bonds between the central metal and the ligands. Second is their geometry. Now we can see the structure. Now Z reacts with this chromium 3 ions Cr plus 3, as the charge is plus 3 on chromium and we have -1 charge on this Z complex. So what will happen that we will need 3 these complexes in order to make it neutral. So 3:1 ratio, it means 1 chromium and 3 Z will react with each other. And in Z we can see we have lone pair on nitrogen atom, we also have lone pair on oxygen atom, so it can behave as a bidentate ligand. You can draw a structure like this. And overall charge will be 0 because chromium is plus 3 and this each is -1. So coordination number is the number of coordinate covalent bonds. As we can see, 6 coordinate covalent bonds are being made with the central chromium. So we can write 6 coordination number, and geometry is octahedral. Part D, NH4(2) Cr2O7 decomposes readily on heating to form Cr2O3, steam and an inert colorless gas. Deduce the oxidation numbers of chromium in ammonium chromate and in Cr2O3. So we have to find the oxidation numbers of chromium. Let's see. First one is NH4 Cr2O7. Overall charge is 0. As we have ammonium, so the charge on ammonium is +1, and we have 2 ammonium, so total charge will be +2. Then we have 2 chromium, so we can write 2 Cr. 7 oxygen, the charge or oxidation state will be -14, so -14 plus 2 becomes -12 equals 0. 2 chromium becomes +12 and 1 chromium will be +6. In Cr2O3 we have 2 chromium, 3 oxygen, the oxidation state of 1 oxygen is -2, so for 3 it will be -6. So chromium, 2 chromium is +6 and 1 chromium will be +3. Next part is the construction of an equation for the thermal decomposition of ammonium chromate. As it already says that it decomposes to form this, steam and inert colorless gas. So we can write the equation. We have NH4 2 Cr2O7. It decomposes on heating to form Cr2O3. Steam is water, and inert colorless gas. Now we have H, hydrogen gas, and it is not inert. We have nitrogen, it is inert gas, so we can write nitrogen. Now balancing the equation, we can see we have 8 hydrogen atoms on the reactant side and 2 hydrogen atoms on the product side, so we can write 4 with H2O. All other elements are already balanced. So this is the final equation. Question 3a part 1, define the term transition element. We can write simple definition. It is an element that forms stable compounds with partially filled d orbitals. Part 2, it says state how the melting point and density of iron it compares to that of calcium. Now we can see that in iron we have 3d orbital that is involved, so 3d electrons are present, while in calcium we have 4s electrons in the outermost shell. So as only 4s electrons are present in or involved in bonding in calcium element, while 3d electrons are present in iron, so number of electron is greater in iron, so stronger electrostatic forces of attraction will be present. And also we can see that calcium is in group 2 while iron is present in transition element, so therefore as we move along the period, what happens is that the size of atoms it decreases. So we can say that the melting point of iron will be high and the density of iron will also be high. B part 1, define the term standard cell potential, E0 cell. Now cell potential is the difference in electrode potential between two half cells, and for standard we have to use standard conditions. So we can write that it is the difference in electrode potential between two half cells. When all solutions present in these two half cells, they obey standard conditions. Standard conditions are 1 mole per decimeter cube solution, 1 atmosphere pressure, and 298 Kelvin temperature. Part 2. Draw a fully labeled diagram of the apparatus that can be used to measure the cell potential of a cell composed of copper 2 copper electrode and iron 3 to iron 2 electrode. Include all the necessary reactants. Now we can see that in first one they have given copper 2 ion and copper solid. There is reduction going on, copper plus 2 it is converting into copper solid, and in second one iron 3, which is ion, is converting into iron 2. So we can draw both cells. In copper one we can use solid electrode, so this electrode is of copper. And it is dipped in a solution of copper 2 positive. The circuit can be connected externally through a voltmeter. On the other side we can see that we do not have any solid electrode, so therefore we can use platinum, porous platinum. And the solution, it will contain iron 3 positive as well as iron 2 positive. And one thing is left, which is the salt bridge. Part C, the reaction between S2O8 -2 aqueous and iodide aqueous is catalyzed by adding a few drops of iron 3 positive. Use equations to show the catalytic role of iron 3 positive in this reaction. Now what happens in this reaction is that S2O8 -2, it converts into 2 sulfate ions, while iodide aqueous, it converts into iodine. Now we can write the equation by the help of this catalyst. First, this catalyst, it will react with iodide. And iodide will be oxidized to iodine. And iron plus 3 is reduced to iron plus 2. In second equation, iron plus 2, it will react with S2O8 and convert that into sulfate, and itself it is again converted back into iron plus 3. Now we can balance this equation. We have 2 iodine on the product side, so we can write 2 with iodide, and 2 iodide needs 2 iron plus 3, and 2 iron plus 2 will be formed. 2 iron plus 2, it will react with this. We have 2 sulfurs, so we can balance by writing 2 on this side. 2 iron plus 3 will be regenerated. Part 2, iron 3 positive can oxidize iodide, whereas iron cyanide -3 cannot oxidize iodide. Use E0 values to explain these observations. Let's write E0 values, which is the reduction potential for iodine when it changes to iodide ions. The reduction potential value is 0.54 volts. For iron +3, when it converts into iron +2, which is reduction, the voltage is 0.77 volts. And for third one, in which FeCN6 -3, it converts to FeCN6 -4. The reduction potential value is 0.36 volts. Now it says that iron +3, it can oxidize iodide. From reduction potential value, we can see that the reduction potential of iron +3 to +2 is 0.77, which is more positive as compared to iodine iodide, which is 0.54. Now what will happen, that the more positive, it means that reduction will occur, and in the other one automatically oxidation will occur. So what will happen, that iron +3, it gets converted into iron +2, while iodide, it will be converted into iodine. Now we can see the reduction potential value of iron CN6 -3, it is 0.36 volts, which is less positive as compared to this one. So reduction will occur here and oxidation will occur in this reaction. So due to this less positive value, it is unable to oxidize iodide. We can write the answer. E0 value of iodine to iodide, which is 0.54 volts, it is more positive than E0 value of iron CN6 to iron CN6. Therefore, it cannot oxidize iodide. Next part, D. When aqueous solutions of S2O8 -2 and tartrate ions are mixed, the reaction proceeds very slowly. However, this reaction proceeds quickly in the presence of iron +3 aqueous catalyst. The overall reaction for this reaction is shown. We have this tartrate ions. It reacts with S2O8 -2 in the presence of water to convert into these products. Suggest why this reaction is slow without the iron +3 catalyst. Now, as in the reaction, we can see that both reactants are negatively charged. So therefore, negative charges, they repel each other. And due to this repulsion, the activation energy of this reaction is very high, and therefore the reaction is slow without catalyst. Now what catalyst does is that it reduces the activation energy by first reducing itself and then oxidizing one of the reactant, and then it gets oxidized back into iron +3. So we can write the answer. S2O8 -2, one of the reactant, and tartrate ions, which is second reactant. They are both negatively charged. So they repel each other and activation energy is very high. Therefore, reaction is slow. Next part 2. Use the overall equation to deduce the half equation for the oxidation of tartrate ions. This one to carbon dioxide and methanoate ions. Now we can look at the full equation. They have given this equation. We have to convert it into half oxidation part. This is the full equation. Now we have to deduce the half equation for oxidation of tartrate ions. We can see that S2O8 -2, there are 3 molecules. It converts into 6 molecules of SO4 -2. We can find out the total charge. -2 is on 1 mole, so for 3 moles it is -6. And for this one, 1 is -2. For 6 moles it will be -12. So it means that going from this part to this part, 6 electrons are gained. So gain of electron is reduction, so this part is reduction. Second part is oxidation, in which we have tartrate ions and they get converted into rest of the products. If 6 electrons are getting gained in these parts, then 6 electrons will be lost in the first one. Let's write the equation. We have C4H4O6 -2, these tartrate ions, plus we have water molecules, and it gets converted into CO2, HCO2, 6H positive, and 6 electrons are lost. Now we can write the values from given equation. We have 2 moles of H2O, 2 moles of CO2 is formed, 2 moles of HCO2, 6 H positive are there, and 6 electrons will be lost. So this is the half equation for oxidation of tartrate ions. E part 1. Complete the following table to show the structures of organic products that are formed when tartaric acid reacts separately with each reagent. Identify each type of reaction. Now we can see this is tartaric acid. We have carboxylic acid groups present. We also have alcohol groups present. First one is the reaction with excess of LiAlH4. Now we know that LiAlH4 is strong reducing agent. And it can reduce carboxylic acid to alcohol. Now this carboxylic acid group and this carboxylic acid group will be converted into alcohol. Now we can say CO2H, it gets converted into CH2OH, which is primary alcohol. Now there are 4 carbon atoms. On all 4 carbon atoms now there will be OH groups attached. And the type of reaction is called reduction. Second is the reaction with an excess of ethanol chloride. Now ethanol chloride, it can react with the alcohol part and gets converted into ester. So now we can make esters with these 2 alcohols. Rest of the structure does not change. Chlorine and hydrogen, it will be eliminated in the form of HCl, and rest of the group will be attached in the form of ester group. Similarly, on this carbon we have oxygen, carbonyl carbon, and CH3. And the type of reaction is called condensation reaction, as small molecule like HCl is eliminated. Next part 2, tartaric acid. It reacts with amine 1-phenyl ethylamine C6H5CH NH2CH3 to form an ionic salt. Draw the structure of the salt formed in this reaction. Include the charges on the ions. Now we can see that in tartaric acid we had carboxylic acid functional groups, and in 1-phenyl ethylamine we have NH2. Now in NH2 we have lone pair on nitrogen, so it can gain a proton. And carboxylic acid, as it is acid, it can lose H positive. So now charges will develop, one will become negative, second one will become positive. So due to electrostatic forces of attraction between positive and negative, it will form ionic salt. We have this structure of tartaric acid. And we have this reactant C6H5CH NH2CH3. Now as only one nitrogen is present, so we need 2 moles of this in order to gain these 2 protons. Now the product will be like this. Both carboxylic acid ends, they will lose 2 protons, and this one will gain 2 protons. One is positive, second is negative, and this is the structure of the salt formed. And there are 2 of these. Question number 4, part A. Samples of copper H2O6 are reacted separately with an excess of aqueous sodium hydroxide or with an excess of aqueous ammonia. Give the following information about these reactions. Reaction 1, we have CuH2O6 with an excess of aqueous sodium hydroxide, color and state of copper containing species. We have to write the ionic equation, and we also have to find the type of reaction. Now let's see, in first reaction, CuH2O6, it reacts with an aqueous solution of sodium hydroxide, so we can write the equation. Ionic equation, CuH2O6, 2 positive, plus we have sodium hydroxide, so it will provide OH negative ions, and this gets converted into copper hydroxide, which is the precipitate, along with water molecules. Now we can balance this equation. We have 6 water molecules on the reactant side. We can write 6 water molecules on the product side. Again, we can see that 2 hydroxide are present on the product side, so we can write 2 with OH negative. Now looking at the charges, on the reactant side we have +2 charge on this reactant and -2 charge for these 2 OH negative ions. So overall there is 0 charge on the reactant side, and again similarly on the product side there is no charge present. Now we have to write the color and state of copper containing species. We have copper hydroxide, which is blue precipitate or blue solid. And the type of reaction is called precipitation reaction because the precipitate is formed. Part 2, reaction 2, CuH2O6 with excess of aqueous ammonia. Again color and state and ionic equation and type of reaction. For this reaction we can write the ionic equation. We have CuH2O6, 2 positive, plus we have ammonia. It will form a complex in which ammonia it replaces water molecules. We have 4 ammonia molecules that replaces 4 water molecules. 2 water molecules are still there. And overall charge is +2. This is because both ammonia and water are neutral, so therefore they do not affect the charge on this copper. Plus water molecules which are eliminated. So out of 6, now 4 water molecules are present. And we can balance ammonia. There are 4 ammonia molecules, so we can write 4 with this one. Overall charges are balanced and the elements and molecules are also balanced. Then we have to write the type of reaction. Now this type of reaction is called ligand exchange. As ammonia is also a ligand and it gets exchanged with water molecule which was acting as a ligand before. Now color in state of copper containing species. Copper H2O6, it gets converted into this complex. Now color is dark blue, so we can write dark blue, and state is that it will be aqueous or solution. Part B, copper 1 oxide is added to hot dilute sulfuric acid, a blue solution X and a red-brown solid Y form. Suggest the identities of X and Y, name the type of reaction. We have copper 1 oxide Cu2O. It is added to hot dilute sulfuric acid. We have H2SO4. Now it will form a blue solution of copper sulfate, which is X, and now we have reddish brown solid. Now in these reactant we can see that the copper is the only thing that is reddish brown in color, so therefore copper is also formed. Now the identity of X is copper sulfate and Y is copper. As we can see that oxidation and reduction has taken place. Copper is +1 on the reactant side as given in the question. On the product side it has converted into +2 and 0. So oxidation has occurred, reduction has also occurred, so therefore we can write that this is disproportionation reaction. Question 5. Dinitrogen pentoxide, which is N2O5, it is dissolved in an inert solvent and the rate of decomposition of N2O5 is investigated. This reaction produces nitrogen dioxide which remains in solution and oxygen gas. Now this is the equation given. We have oxygen gas which has been formed. Suggest what measurements could be used to follow the rate of this reaction from the given information. Now we can find the rate of reaction by using the volume of gas, as we know that gas is formed. So the volume of gas produced per unit time, it will give us the rate of this reaction. So we can say that the volume of oxygen formed it can be measured against time taken to find rate of chemical reaction. Part B, in a separate experiment, the rate of decomposition of N2O5 gas is investigated. This is the equation. Again, oxygen gas and NO2 gas has been formed. The graph shows the results obtained. Let's look at the graph. On y-axis we have N2O5 in mole per decimeter cube. The concentration is given. On x-axis we have time, and we can see that as time goes on, the concentration of N2O5 decreases. The reaction is first order with respect to N2O5. This can be confirmed from the graph using half-lives. Explain the term half-life of a reaction. Half-life, it is the time taken for amount of reactant to fall to half of its original value. As we can see from the graph that this is the concentration of N2O5 and it was 0.25, so from 0.25 to 0.125 it will be half of the concentration and the time will give the half-life. Part 2. Determine the half-life of this reaction. Show your working on the graph. Let's move back to the graph. Now we can choose any value from the graph. Let's choose this one, 0.20. Half of 0.20 will be 0.10 and half of 0.10 will be 0.05. This is the center one and it is at 50 seconds. This one is at 200 seconds. It is in between 300-400 and it is 350 seconds. Now we can find the difference between these. From 50 to 200, the difference is 150 seconds. From 200 to 350, again the difference is 150 seconds. Now we can see that the time is same for half-life, so therefore this reaction is first order reaction. Now the half-life is 150 seconds. Suggest the effect on the half-life of this reaction if the initial concentration of N2O5 is halved. Now half-life is independent of the initial concentration of N2O5, so therefore we can say that there is no change on half-life. Part C. Use the graph in 5 Part B to determine the rate of reaction at 200 seconds. Show your working. We have to find the rate of reaction and we also have to find the units. Rate equation for the reaction is shown. Rate is equal to K into N2O5. Now for rate of reaction we know the formula. Rate is equal to change in concentration divided by time taken. Let's find out the rate at 200 seconds from the graph. Now this is the value at 200 seconds. We can draw tangent to find out the change in concentration and the time taken. Now this is the tangent that is drawn and it is going exactly through this point at 200 seconds. Now we can find the change in concentration. It is 0.20 and 0. So the change in concentration is 0.20 mole per decimeter cube. On x-axis we have time and we can see that it starts from 0 to 400. So therefore this is 400 seconds. Now we can use these values to find out the rate of reaction. It will be 0.20 divided by 400. It is equal to 5 exponential minus 4. Now the units change in concentration is in mole per decimeter cube and time taken is in seconds, so it will be mole per decimeter cube per second. Use your answers to see part 1 to calculate the value of rate constant K for this reaction and state its units. We can find out the value of K. K will be equal to rate of reaction divided by the concentration of N2O5. So we have to use the answer in C part 1. We can use the value of this for rate. So rate is equal to 5 exponential minus 4. And we have to find out the concentration of N2O5 at 200 seconds. Let's look into the graph. At 200 seconds, the concentration of N2O5 was 0.10 mole per decimeter cube. So we can divide by 0.10 mole per decimeter cube, and the values will come equal to 5 exponential minus 3. As we already have the unit for rate, which is mole per decimeter cube per second. Concentration is in mole per decimeter cube, so divided by mole per decimeter cube. Now both mole per decimeter cube, they get cancelled and only per second is left. So therefore the unit is per second. Part D, nitrogen dioxide reacts with ozone as shown. NO2, it reacts with ozone to form N2O5 and oxygen. The rate equation for this reaction is rate is equal to K into NO2 into ozone. Suggest a possible two-step mechanism for this reaction. You can write any mechanism as long as it is consistent with these reactants and this product. In this equation we can see we have 2 moles of NO2, 1 mole of ozone, 1 mole of N2O5 and 1 mole of oxygen. As we have 2 moles of NO2, so we can use this one in both equation or both steps. This is the first step and this is the second step. Now the reactant is NO2 plus ozone. And the final product is N2O5 plus oxygen. So we have to find out this product and then use this product in order to make this one. So now we can use this reaction. NO2, it can react with ozone to form NO3. 1 oxygen is gained from ozone along with O2. And this NO3, it can react with this NO2 to form N2O5. And this oxygen is already formed, so we can remove this one. So now we have NO2 plus ozone. In the first step it forms NO3 plus oxygen, and in second step NO2, it reacts with NO3 to form N2O5. Now we have 2 moles of NO2, 1 mole of ozone and 1 mole of this product along with 1 mole of oxygen. Question 6, Part A, compare and explain the relative acidities of butanoic acid, ethanol, ethanoic acid and water. We can draw the structures. First one is butanoic acid. In butanoic acid we have CH3, CH2, CH2, then C double bond O, OH. Then we have ethanol. In ethanol we have CH3, CH2, OH. Then ethanoic acid, CH3, C double bond O, OH. And last one is water, which is neutral. Now acidity, it depends on the strength of this OH bond. Stronger OH bonds means less acidic, as less H positive ions will be released, and weaker OH bonds means more acidic, as more H plus ions will be released. Let's see which molecule has the weakest OH bond. In butanoic acid we have this propyl group that is attached, and due to positive inductive effect of alkyl group, what will happen that it will provide electrons to this carbonyl carbon and oxygen, so therefore this bond will be strengthened. And in second one we can see we have just one methyl group attached, so positive inductive effect is still there but it is less as compared to this one, so therefore this bond is more strong as compared to this bond. So among carboxylic acids, ethanoic acid will be more acidic as compared to butanoic acid. Second thing is the comparison of carboxylic acid with alcohol. Now we can see that in carboxylic acid we have carbonyl carbon, and due to negative inductive effect of this oxygen it can weaken OH bond. But there is no carbonyl carbon or negative inductive effect in alcohol, so therefore alcohol is less acidic as compared to carboxylic acid. Now we can say that ethanoic acid is the strongest acid as there is less inductive effect as compared to butanoic acid. And butanoic acid is more acidic as compared to alcohol because there is positive inductive effect of this alkyl groups and it strengthens this OH bond. In the last one we have water, which is neutral. So we can write that the acidity of carboxylic acid is due to negative inductive effect of this carbonyl carbon and among these two carboxylic acids more positive inductive effect is seen in butanoic acid due to longer chain as compared to ethanoic acid. For alcohol we can say that due to positive inductive effect in alcohol OH bond is strengthened. Part B, 3 carboxylic acids, methanoic acid, HCO2H, ethane dioic acid, we have 2 carboxylic acid groups, and butane dioic acid are compared. 2 tests were carried out on separate samples of each organic acid as shown. Following results were obtained. Tick means observed change and cross means no observed reaction. In the first one we have to find out the reagent which can react with HCO2H but it does not affect dicarboxylic acid or butane dioic acid. So now we can see that if we use mild oxidizing agents such as Tollens reagent or Phelan solution, it can only oxidize methanoic acid. Only methanoic acid is oxidized and there is observed change that if we use Tollens reagent then silver mirror is formed. If we use Phelan solution then brick red precipitate will be formed. Now these mild oxidizing agents, they cannot oxidize dicarboxylic acid or butane acid. Now if we use acidified KMnO4 and warm the solution, it can oxidize methanoic acid as it is the easiest to oxidize, and it can also oxidize ethandioic acid to carbon dioxide and water molecules. So only these two will be oxidized, and KMnO4, the color will be decolorized. Part 2, each compound HCO2H, methanoic acid, ethandioic acid and butanedioic acid is dissolved separately in CdCl3. Proton NMR and carbon-13 NMR spectra are then obtained. Complete this table. We have to find out number of peaks in proton NMR and number of peaks in carbon-13 NMR. Let's draw the structures of all these three. We have HCO2H. Second is we have two carboxylic acid groups. In third one we have butanedioic acid. Let's first find out carbon-13 NMR peaks. In HC double bond OH we can see that we only have one carbon present, so there will be just a single peak in carbon-13 NMR of this compound. In second one we can see that we have two carbon atoms present. One is this one is this one. And as we can see that both carbon atoms are double bonded with the oxygen and single bonded with OH. So they are exactly similar because the molecule is symmetrical. So both will give the same peak, so therefore just single peak is obtained. In third one we can see that we have again COOH on both sides and both are exactly similar because the molecule is symmetrical. And then we have these two carbon atoms that are present in the same environment because both CH2 are attached to COOH. This one is also attached to COOH and both are attached to each other. So we have one peak from these two and one peak from these two. So overall 2 peaks of carbon-13 NMR will be seen. Now let's find out about proton NMR. Let's look at protons. We have hydrogen. This hydrogen is different as compared to this one because it is directly bonded to oxygen while this is bonded to carbonyl carbon. So we have 2 peaks in this NMR spectrum. Looking at the second one, we only have this hydrogen atom which is bonded to oxygen, which is bonded to carbonyl carbon. And again this one is exactly similar, so therefore only a single peak will be observed as both protons are in same environment. In third one again we have these two which are similar because both are part of carboxylic acid groups, and these two hydrogens are similar to these two hydrogens, so they will give one peak and these will give one peak. So overall 2 peaks will be observed. Part 3, the proton NMR spectrum of methanoic acid in D2O is obtained. Describe and explain the difference observed when this spectrum and proton NMR spectrum of HCO2 in part B2. Now what D2O does is that it exchanges deuterium instead of hydrogen. So now in HCO2H we had 2 peaks of proton NMR because these two hydrogens were present in different environments, Now what will happen, that this OH, it will be exchanged with deuterium. So as D does not show peak in NMR spectrum, so therefore one peak will be eliminated and only one peak will be left behind. So we can say that OH peak in methanoic acid will disappear, due to proton exchange with deuterium oxide. Now this can happen both for OH group and also for NH. Part C, 1,4-dibromobutane BrCH2,4-Br is used in synthesis of dicarboxylic acid J and diamine K as shown. This is the given compound, and in step 1 it converts into G, which then converts into J, and in step 3 it converts into H, which then converts into K. Let's see the structure of both J and K. In J we have 4 carbon carboxylic acid, and in K we have 1, 2, 3, 4, 5, 6 carbon diamine. Part 1, draw the structures of G and H in the boxes. In the reactant we have 1, 2, 3, 4 carbon atoms present, 2 bromine atoms are present, and in J we can see we have 1, 2, 3, 4 carbon atoms are present, and bromine is replaced with carboxylic acid groups. So now what we can do is that first we can convert bromine into alcohol, or we can replace Br with OH. So it will be converted into CH2, 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 and both Br will be replaced with alcohol groups. Now these alcohol groups, they can be oxidized in step 2 to form carboxylic acid. Now let's look into the product K. In K we can see we have 6 carbon atoms present, while in the reactant we only had 4, so we can increase the number of carbons by using Cn. One Cn can add 1 carbon atom, so therefore we can add 2 Cn to these 2 corner carbons. The product will be like this. We have 4 carbons in the center. 1 Cn group will be attached to this corner carbon, 1 Cn group to this corner carbon. Now we can reduce this nitrile groups into primary amines. Suggest the reagents and conditions for each steps 1 to 4. In step 1 we have replaced Br with OH, so therefore we can use aqueous sodium hydroxide along with heat. In step 2 we can see we have converted alcohol to carboxylic acid, so therefore we have oxidized this one, so we can use acidified KMnO4 along with heat. We can write these two. Step 1 is aqueous sodium hydroxide plus heat. Second one is acidified oxidizing agent KMnO4 plus heat. You can also write K2Cr2O7 plus heat. Let's look into step 3. In third step, we can see we have changed bromine to cyanide or nitrile. Now we can use cyanide ions from sodium cyanide or potassium cyanide along with heat. In step 4, we have reduced this nitrile to primary amine, and it is a reduction with LiAlH4, which is powerful reducing agent. We can write these two. And the last one, we had used powerful reducing agents such as lithium, aluminum hydride. Per D, polyamide L can be synthesized from dicarboxylic acid J, this one, and diamine K, this one. Draw the repeat unit of the polymer that is formed in the box. Any functional groups should be shown displayed. We have these two. First one is J. We can draw the structure. We have carboxylic acid. Then two CH2 are present. Carboxylic acid on the other end. And in K we have diamine, NH2 on one end. Then there are 6 CH2 and then NH2 on the other end. Now we can see that when both of these will react to form polyamide, what will happen, that condensation reaction will occur and OH is removed from carboxylic acid group and hydrogen is removed from amine group. So it will be eliminated in the form of H2O. Similarly, this hydrogen goes with the next OH group from carboxylic acid, and this OH from carboxylic acid goes with the hydrogen from amine. So rest is the structure of polyamide. We can start from this bond. We have carbonyl carbon, then 2 CH2. Now functional groups should be displayed. Now we have this nitrogen. A hydrogen atom is also present. And so on. Now we can see that from carboxylic acid and amine, amide is formed. Question 7, Part A, 3-amino-benzoic acid can be synthesized from methylbenzene in 3 steps. We have methylbenzene. In step 1 it is converted into M, then in step 2 it is converted into N, and in step 3 it is converted into 3-amino-benzoic acid. Now it says that draw the structures of M and N in the boxes. Suggest reagents and conditions for each step of the synthesis. We have 3 steps and we have to find out the reagents as well as conditions. We can see the starting product as well as the end product. In starting product we have methyl group, which is CH3 attached directly to benzene ring. And in final step we can see that this methyl group is no longer present. A carboxylic acid group is present. So it means that this side chain is oxidized into COOH. Second thing is the presence of NH2 amine group, which is introduced into the benzene ring. Let's first convert this side chain into carboxylic acid. So in step 1 we can oxidize methylbenzene in the presence of hot KMnO4. And this side chain will be oxidized to COOH. There is no effect on benzene ring. In step 2 now we can do something about the side group. First we can add nitro group and then we can reduce that nitro group in step 3. Now in step 2 we need NO2 positive And to generate NO2 positive, we need concentrated H2SO4 and concentrated HNO3. Both of these react together to form NO2 positive, which is electrophile, along with HSO4 negative and H3O positive. NO2 is generated, which then adds up in this benzene ring. Now carboxylic acid group is 1, 3, 5 directing. So therefore the incoming electrophile, it will be attached to either first position, which is already occupied, or third position or fifth position. So now we can add it to third or fifth position. Now NO2 is added into the benzene ring. In step 3, we can now reduce this NO2 group to NH2. Now we can use a reducing agent, for example tin, in the presence of concentrated HCl along with heat. It will form water and NO2 group is converted into NH2. We can write the reagents and conditions in these lines. In step 1, we used hot KMnO4. In step 2, we used concentrated sulfuric acid and concentrated nitric acid. In step 3, we used tin, concentrated HCl along with heat. Part B, a mixture of serine, which is this one, OH, CH2, CH, NH2, COOH, and lysine. We have this structure, reacts to form several different products. Draw the structures of the two structural isomers with the molecular formula C6H12N2O5 that could be present in the product mixture. The functional group formed in each case should be displayed. In the given mixture, we can see we have alcohol functional group, we have amine functional group, carboxylic acid functional group, again NH2, this one is similar, and carboxylic acid functional group. They have given the molecular formula of the product and two structural isomers are formed for this molecular formula. We can write the molecular formula. We have 3 carbon atoms in this structure, 7 hydrogen atoms, and 3 oxygen atoms, 1 nitrogen atom. Similarly, in this one we have 6 carbons, 14 hydrogens, 2 oxygens, 2 nitrogen atoms. Now let's look at this product. We have 6 carbon atoms. Now this product can be formed if 2 serine molecules, they react with each other. Each has 3 carbon atoms, so it will become 6 carbon atoms. So for example, we have first serine C3H7O3N. It reacts with another serine molecule C3H7O3N. And when these two will react together, they will react by condensation reaction, as we have carboxylic acid functional groups and amine and alcohol groups present. So water molecule is also released. When H2O is released, so 2 hydrogen and 1 oxygen will be less as compared to this molecular formula. So total carbon will be C6, total hydrogen will be 14, and minus 2 it will be 12. Oxygen should be 6, but 1 is removed, so it is 5, and nitrogen are 2. As we can see that this is similar to this one, so it means 2 serine molecules should be involved in formation of this one, and we can draw the 2 structural isomers. Now the first one is OH, CH2, CH, then we have NH2, then COOH. Second one will be similar, OH, CH2, CH, NH2, COOH. Now what can happen is that as we have different functional groups, so OH functional group from one molecule, it can react with carboxylic acid functional group from other molecule to form ester. Or we can also say that carboxylic acid group from one molecule, it can react with NH2 group of second molecule to form amide. In both cases, water molecules will be released and molecular formula of the product would be this one. Let's first draw ester. We can take this carboxylic acid and this alcohol group, make out an ester from these two. So now it will be OH, CH2, CH, NH2. Then we have this ester group, as OH and H will form water. And then we have CH2, CH, NH2 and COOH. Now we can also use these two to form amide group. Let's take this carboxylic acid group and this amine to form amide. Now the structure will be OH, CH2, CH, NH2. Then we have COOH. OH will be removed along with this hydrogen. So C double bond O will be left. And now we have this nitrogen and along with only one hydrogen. Then we have this CH group, which is now branched. On one side we have CH2OH, on second side we have COOH. We can also draw the skeletal formula starting from this carbon. Then we have this carbon, then carbonyl carbon, then we have oxygen, then again this carbon, this CH, along with this one we have NH2 and then COOH. With first carbon we have OH group, second carbon we have NH2, with third carbon we have oxygen, with fourth carbon we have two hydrogen atoms, with fifth carbon we have NH2, and rest is similar. Similarly, we can draw a structural formula for this one. Starting from this carbon, then CH, then carbonyl carbon, then nitrogen, then again CH. It is branched into two, one is COOH and one is CH2OH. Now we can write the remaining substituents. On first CH2 we have OH group. On second CH we have NH2. Third is carbonyl, fourth is nitrogen, and with nitrogen we have one hydrogen atom. Then we have CH, CH2, OH and COOH. Now both of these are structural isomers. In the first one we have ester functional group and second one we have amide functional group. The molecular formula of both is C6H12O5N2. Part 2, predict the number of different structural isomers with the molecular formula C9H19N3O4. that could be present in the product mixture. We have to find out the structural isomers for this molecular formula. Now in the reactants they have given one with 3 carbon and second with 6 carbon, so it means we have to join these two together to form 9 carbon atoms. So now we can rewrite, first one is C3 H7O3N, second one was C6 H14 O2N2. Now when both of them are added together, what will happen, that condensation reaction will take place and water molecule is also released. Now we have 9 carbon atoms, 6 and 3 becomes 9, 14 and 7 is 21 minus 2 hydrogen, so it will be 19 hydrogens. Then we have 5 oxygen atoms, out of which one is lost in water, so we have 4 oxygen atoms and 3 nitrogen atoms present. So this is similar to this one. So it means that we can make isomers between these two, one is serine and one is lysine. Let's write the structures. First one is serine, serine is OH. Then we have CH2, CH, then NH2, COOH. In second one we have 4CH2, then CH and COOH. NH is present on this one and one NH2 is present in the start. So now we can see we have different functional groups. Let's look. First one is alcohol. Now this alcohol can react with carboxylic acid to form ester. Then we have NH2 group. NH2 can react with this carboxylic acid to form amide. Then we have this carboxylic acid which can react with this NH2 to form another amide. And we can see that this carboxylic acid can also react with this NH2 to form another amide. In each one we have chosen just one functional group so that one water molecule is released and the molecular formula will be this one. So in total we have 4 number of structural isomers that are formed through this molecular formula. Part C, glutathione is a naturally occurring compound found in plants. This is the structure. On the diagram of glutathione, label each chiral center with an asterisk. Now chiral carbon is the one that is bonded to 4 different groups or elements. If we have any carbon that is bonded to 2 hydrogen, it is not chiral. If we have any carbon that is making double bond, it is not chiral. Let's look into the structure. This carbon is making double bond, so it is not chiral. This carbon has 1 hydrogen atom also present. So one group is this one is hydrogen, one is NH2 and one is this whole group. So this one is chiral carbon. Moving towards next, this carbon has 2 hydrogens, so it is not chiral. Again 2 hydrogens, again double bond. Then looking at this carbon, we know that also a hydrogen atom is present. So one group, second group, and this whole is third group and this whole is fourth group. So yes, this carbon is also chiral. This carbon is double bonded. This carbon has 2 hydrogen atoms. This is double bonded. So we only have 2 chiral carbons present. Now we can draw an asterisk with each. Part 2, draw the structures of the 3 products formed after complete acid hydrolysis of glutathione assume the thiol group SH does not react. In this given structure, we can see we have this linkage C double bond O NH, which is amide linkage. Again we have C double bond O NH, which is amide linkage. No ester linkage is present. So amide linkage, it can be hydrolyzed by acid. So on complete hydrolysis, amide linkage is converted into carboxylic acid group and amine. So we can break these two bonds. One is this one and one is this one. So we have three products. This is the first part. Between these two, this is the second part. And after this one, this is the third part. So let's draw first one. We have C double bond O OH. Then we have carbon with NH2. Then again two carbon atoms are present, 1, 2. Then this carbonyl, which gets converted into carboxylic acid. This is the first part. Now moving towards second part in between these two breakings. So we have to start from this nitrogen, so it gets converted into NH2. Then we have this carbon, which is attached to CH2SH. This carbonyl carbon gets converted into carboxylic acid. Now third part will be COOH, CH2, NH2. So we have C double bond OOH, then CH2, then NH2. Part 3, glutathione is soluble in water. By referring to the structure of glutathione, explain why it is soluble in water. We can see in the structure, we have C double bond OH group on one side, we have C double bond OH group on the other side. We also have NH2 group present. So therefore these groups, they can form hydrogen bonding with water, and carboxylic acid can also dissolve in water. So we can say that due to the presence of carboxylic acid functional groups, and NH2 group, it can form hydrogen bonding with water. Therefore it is soluble. Question 8 part A. This sketch graph for the titration of ethanoic acid with sodium hydroxide is shown. This is the pH and this one is equivalence point. Volume of sodium hydroxide is on x-axis. Part 1. In the region circled on the graph, identify the two organic species that are present in the solution. Explain why the pH of the mixture only changes slowly and gradually in this region when sodium hydroxide is being added. Now we can see that there is slow increase of pH when sodium hydroxide is added, and then there is abrupt change in pH. First, we can identify the two species present. One is ethanoic acid, CH3COOH. Second reactant is sodium hydroxide in titration. So now it will form sodium salt of ethanoic acid, sodium ethanoate, along with water. Now sodium ethanoate is soluble salt, so it will be dissociated into two parts, CH3COO negative and Na positive. As the amount of sodium hydroxide is less, as the volume added is still less in this region where the circle is given, so therefore we have excess of CH3COOH. We also have this product that is formed. So two species present are CH3COOH, ethanoic acid, and ethanoate ion. Now second part is that why pH of the mixture only changes slowly. This is because the hydroxide ions that are provided with from sodium hydroxide, they can react with H positive ions from this weak acid to form water. So as hydroxide ions are continuously converting into water, so therefore there will be a little change in pH. So we can write the answer. This is due to buffering action. CH3COOH, it can react with sodium hydroxide to form CH3CO2 negative, as we have done in this equation, and water. Now you can also answer it like this, that CH3COOH, it will be dissociated to form H positive ions, and then those H positive ions, they will react with OH negative from NaOH to form water. OH negative from sodium hydroxide react with H positive ions produced from ethanoic acid, and equilibrium shifts to the right direction. You can show the equilibrium with an equation. CH3COOH it dissociates to form CH3COO negative along with H positive, and OH negative from sodium hydroxide, they react with this to form H2O. So now as product is being consumed into water, so therefore this equilibrium will shift to the right direction. So then more H positive ions will be formed and more OH negative ions will be converted into water, so therefore there is less change in pH. Part 2, the equivalence point in this acid-base titration is where the two solutions have been mixed in exactly equal molar proportion. Just suggest why the pH is greater than 7 at the equivalence point in this titration. Now equivalence point is the point at which all H positive ions from acid, they react with OH negative ions from alkali to form water and gets neutralized. But the equivalence point is not always at pH 7. This is because of the reactants present. Now in this reaction we have CH3COOH. Now what happens that CH3COOH, it gets converted into CH3COO negative and H positive. This H positive will be consumed with sodium hydroxide to form water at equivalence point, but still this is present in the solution. And this ethanoate ion is a strong base because it can react with water to form hydroxide ions. For example, CH3COO negative, it can dissociate water molecules to again form CH3COOH and release OH negative ions. Due to the presence of this OH negative ions, at equivalence point the pH is still greater than 7 and pH is about 9. So we can say that CH3COO negative is relatively strong base and is still present at equivalence point. It reacts with water forming OH negative ions which increase pH to 9. Part B, an impure sample of ammonium vanadate NH4VO3 with mass of 0.150 grams is dissolved in an excess of dilute acid. In this solution, all vanadium is present as VO2 positive. An excess of zinc powder is added to solution and all the VO2 positive ions are reduced to V+2 ions. The mixture is then filtered to remove any remaining zinc powder. When the resulting solution is titrated to 20.10 cm cube of 0.0250 mole per decimeter cube, acidified manganate oxidizes all V+2 ions back to VO2 positive ions. This is the equation given. Calculate the percentage by mass of NH4VO3 in the 0.150 gram impure sample which was given of NH4VO3. Give your answer to three significant figures. So we can say that we have impure sample of ammonium vanadate NH4VO3 and it is 0.150 grams. Then this is dissolved in excess of dilute acid. We have dilute HCl in excess and also zinc is present, zinc powder which is added. So now it gets converted into V+2. We have to find the percentage by mass of ammonium vanadate in this impure sample. Now this V+2, it is then titrated with acidified manganate and it gets converted back into VO2 positive. So first we can find the number of moles of this acidified MnO4 from this given value. Then we can find V+2, then back to VO2 positive and then back to VO3 positive and then to ammonium vanadate. So we can do it one step at a time. Let's find number of moles. Number of moles is equal to concentration into volume in decimeter cube. This is centimeter cube, so it should be divided by 1000. Now putting values, concentration is 0.0250 into 20.10 divided by 1000. So number of moles of this MnO4 negative, it comes equal to 5.025 exponential minus 4 moles. Now this MnO4 5.025 exponential minus 4 moles, it reacts with V+2. Now we can see that in this equation V+2 is not given. This is the equation only for the reduction of MnO4 negative and this is the equation of V+2. But in these equations the number of electrons are not balanced. So we can balance the number of electrons. We can multiply this equation with 5 and this one with 3 so that both equations are balanced. Both will form 15 electrons which are then cancelled out. Now with MnO4 negative it comes a 3. So we have 3 MnO4 negative. And with V2 positive there comes a 5. So it means 3 moles of MnO4 negative, it can react with 5 moles of V2 positive. So we have MnO4 negative. We have V2 positive. So according to balanced equation, 3 moles of MnO4 negative, it requires 5 moles of V+2. As we have this much moles of MnO4, now we can find the number of moles of V plus 2 by cross multiplying. So now the number of moles of V plus 2, it comes equal to 8.375 exponential minus 4 moles. Now we can see that this V2 positive, it was formed from VO2 positive, which was formed from VO3 negative. So all of them have same number of moles. V2 positive, which we have calculated, it is similar to VO2 positive. It is similar to VO3 negative. So if this one is 8.375 exponential minus 4, then this one should also be 8.375 exponential minus 4 moles. Now we can find the mass. Formula for mass is equal to moles into molecular mass. And now we have to find the mass of ammonium vanadate. It will be equal to number of moles multiplied by the molecular mass of this whole. It is 116.9. So mass of ammonium vanadate, it comes equal to 0.0979 grams. Now this is the mass of pure NH4VO3. We have 0.150 gram impure sample, so let's find the percentage by mass. So percentage purity or percentage by mass, it is equal to mass of pure sample divided by mass of impure sample into 100. Mass of pure sample is 0.0979. Impure sample is given 0.150 into 100. So percentage by mass comes equal to 65.3%. So we can write 65.3%, and there are three significant figures. Question number 9. The carbon-13 NMR spectrum of compound A, which is C8H8O2, contains 6 peaks. Compound A reacts with an excess of bromine water to give compound B. Bromine is added. Compound A reacts with alkaline aqueous iodine to form a yellow precipitate C and compound D. D reacts with PCl5 to form compound E, in which chlorine is added. Compound E reacts with propane 2-ol to form compound F. You have to draw the structures of compound A to compound F in the boxes. This is the molecular formula of compound A. It contains 6 peaks, which means that there are 6 different environments of carbon which are present. Then we have first reaction. It reacts with excess of bromine water to give this compound. And in this compound we can see we had 8 hydrogen atoms, out of which only 6 are now present and 2 hydrogen atoms are replaced with 2 bromine. Now it is not in alkene. In alkene there is always addition reaction and hydrogen atoms are not changed. So it could be benzene ring, as substitution can take place in benzene. So we can say benzene is present. Then compound A reacts with alkaline aqueous iodine to form yellow precipitate. It means that either this is present, because when methyl group is directly attached to carbonyl carbon, it gives positive result with alkaline aqueous iodine. Or we can also have secondary alcohol group CH3COH. It could also be present because it gives positive results with alkaline aqueous iodine. Let's draw the structure of A. First we can do this one. We have CH3, C double bond O, and then we can draw benzene. Let's find out the molecular mass. We have 2 plus 6, 8 carbons. We have 1, 2, 3, 4, 5 hydrogen, 6, 7, 8 hydrogens. We have 2 oxygens. In this structure, we only have 1 oxygen. Now we can try the second one, CH3CHOH, CH3CHOH, then benzene ring. Now we have 6, 7 and 8 carbon atoms. We have 1, 2, 3, 4, 5 hydrogen in benzene, 6, 7, 8, 9, 10. Now we have only 8 hydrogen atoms, not 10, so therefore this structure is also incorrect. So we can tweak this structure in order to add one more oxygen without changing the number of hydrogen atoms. So we can add oxygen in the form of OH group, and when it is substituted to benzene, what will happen, then one hydrogen will be replaced with this OH group, so number of hydrogen atoms will not change. It will still be H8. So we can add OH on this carbon, or you can add OH on any other carbon. So we have this structure now, CH3, C double bond O, benzene, OH, or we can add OH to any other carbon atom. For example, CH3, C double bond O, for example this one. Let's find the environments of carbon. We have this CH3, which is different as compared to this carbon, which is different as compared to this carbon, because this carbon does not have any hydrogen atoms present. These two carbon atoms are exactly similar, as both are CH and both are attached with this carbon. Similarly, these two carbon atoms are exactly similar. So we have 1, 2, 3, 4, 5 peaks, and we have this carbon left, and in total we have 6 carbon 13 NMR peaks. So this structure looks promising. Let's look at this one. We have CH3, 1 peak, then this carbon, second peak, then this C, third peak. Now these two are not similar because this carbon is attached with CHOH while this carbon is attached with only CH. So this one will give fourth peak, this fifth peak, and this one is different. It will give sixth peak. Then we have seventh one and eighth one. So we have 8 carbon 13 peaks, which is wrong. This is because now the symmetry of benzene is disturbed, so it will give more than 6 peaks. So if you add OH group to any other carbon atom other than this one, it will give more than 6 peaks. This is incorrect. So now we can continue with the first structure. We can remove others. Next reaction is with bromine aqueous. Now bromine aqueous, what happens is that 2 hydrogen atoms, they are replaced with 2 bromines and other things are not changing. So now as we have OH group present with benzene and OH is 2, 4, 6 directing, it means that incoming electrophile will be either attached to second position or the fourth position is already occupied. So for fourth there is nothing going to be attached, or sixth position. So we can draw the structure. We have CH3, C double bond O, then benzene ring. As we have 2 bromine attached, so one will be at second position, second will be at 6th position. OH is still present. Let's move forward in this direction. We have alkaline iodine, so yellow precipitate is formed. As we have methyl groups, so it will form CHI3, which is yellow precipitate. And the other part of this will be carboxylic acid attached to benzene ring. So we have benzene, we have OH, we have C double bond O, OH. Now we can see that we can convert this carboxylic acid to acyl chloride in the presence of PCl5. What will happen that this OH, it gets replaced with chlorine. Now the structure will be like this. We have benzene, OH, C double bond O, Cl. Let's count the number of carbon atoms. 6 in the ring and this one is 7. Then we have 5 hydrogen, 4 in the ring, 1 on OH, 2 oxygen and 1 chlorine. Moving towards the next part, we have propane 2-ol. Propane 2-ol is like this. We have CH3, CH, CH3, 3 carbon alcohol. Now what can happen is that this acyl chloride, it can react with this alcohol to form ester. In a condensation reaction, HCl will be removed. Now we can draw the structure. We have benzene, OH, carbonyl carbon, and now with this carbon, this oxygen will be bonded. And with this oxygen, we have 3 carbon atoms that are attached, so we can make a triangle. 1, 2, 3 carbon atoms attached with oxygen, plus this HCl molecule that will be removed. Thanks for watching. If this was useful, please do like, subscribe and share.